Okay, we were discussing about the multi-resolution analysis in the last class. So what we have discussed is that we have started from a scaling function phi t, and then we have seen that, okay, let us define a space v naught as span of phi kt over k. It means this is the set of all the functions which can be generated from phi kt, and phi kt is nothing but phi of t minus k simply. So you are simply translating this function phi t with some integer index in time. So phi t minus 1, t minus 2, and so on. Okay, and then we have seen that how you can increase the space of this function phi t by changing the scale of this function. So we have changed phi kt to phi of jkt. Okay, so where we have scaled it by factor of 2 raised to power j t minus k, and we have defined Vj as the space or the span of phi jkt over k, or you can say the set of all the functions which can be represented by these functions. Okay, so if j is 0, so 0 scale, so you get just phi kt. So there is only scaling, and so there is only translation, no scaling. So if it is v1, so v1 is basically the set which can be generated from phi to t minus k, j is equal to 1 scale. Similarly, v2 by phi of 4t minus k, and so on. Okay, so we have a nested loop of spaces in that case. So we have seen that, okay, v naught is basically a subset of v1, which is a subset of v2, and so on. Similarly, v of minus 1 is a subset of v naught. Okay, so what it means is that if a set of functions can be represented by phi kt, so those functions can also be represented by phi of 2t minus k. Okay, so if v naught is the space of phi kt, so v1, of course, the space or the span will be large as compared to v0. So v0 space is a subset of v1. Okay, and we have taken this example from this Haar function. So we have defined the Haar scaling function like this. So it is a unit length, unit height function phi t. This is called as Haar scaling function. So if it is phi t, then you have phi t minus k, okay, it is shifted by 1. Phi t minus 2 shifted by 2 to the right, and so on. This is how you can generate phi of t minus k. But when you generate phi of 2t minus k, if k is 0, it is only phi of 2t, so it is compressed by half. If it is phi of 2t minus 1, it is shifted by half. So this function is phi of 2t minus 1. Okay, this one. And this is phi of 2t. So by using phi of 2t and phi of 2t minus 1, it means this original function is scaled by half and it is shifted by half. Then when you have phi of 4t, it will be compressed by a factor of 4. So it is compressed by a factor of 4 and shifted in a time intervals of 1 by 4, 1 by 4, 1 by 4, and so on. Okay, now since phi t can be generated from phi of 2t, it means whatever functions or whatever is the space of v naught, that will definitely be a space of v1. Or moreover, the space of v1 will be large as compared to v0. It means you can generate more functions by using these two functions than only using this function phi of t. So based on this discussion, we have an equation that, okay, if you say that if v1 is a or v0 is a subset of v0, it means this phi t, it should be expressed in terms of phi t only. So I have written an equation for that summation of n square root of 2h0n phi of 2t minus n, which is a very important equation, which is called as refinement equation. Okay, and for Haar filter or for Haar wavelet, we have seen that, okay, for this equation to satisfy, or the solution of this equation is h0 0 is 1 by root 2 and h0 1 is 1 by root 2, which is called as scaling filter. Okay, so for multi-resolution analysis, this is very important that the wavelet or the scaling function should be expressed in terms of its own scales and translates using a refinement equation. And then we have introduced the concept of wavelets, a function defined by psi t. So what we have done there is that, okay, if we have this nested loop of space, this is space of v0, this is space v1, then v2, v3. Okay, so instead of using only the scaling functions, we use this wavelet function, which is basically used to span the difference between the spaces that is left by the scaling functions. Okay, or suppose if v1 is the space, this is the space of v1, entire space. Okay, and some part of this v1 is basically spanned by v0, which is a subset of v1. So rest of the space, this much, which is not covered by the scaling function, this is basically covered by wavelets. Okay, so v1 we have seen that, okay, v1 can be, the space of v1 can be covered using v0 and w0, and similarly v2, it can be covered using v1 and w1, and since v1 is v0 union with w0, so you can write it as like this. Okay, so anyhow, in the L square, the entire L square space, it can be covered using a single scaling function at scale j is equal to 0, and the rest of will be the wavelets. Okay, this is what is multi-resolution analysis that we have discussed. Okay, and we explained this that, okay, v1, if you have v1 which is v0 with w0, so if you take scale j is equal to 0, what is the basis function in this space v0? It is a simple scaling function. So for a Haar wavelet, it is a rectangular pulse of unity height and unity width. So it is 0, it is 1 here, the height is also 1. Okay, so this basis function will span this space v0. Similarly, w0, what will be the basis function for this? It is the mother wavelet. Okay, so Haar wavelet, it is like this. Zero, 1 by 2, 1. This is 1 and this is minus 1. Okay, this is for j is equal to 0 scale, and for j is equal to 1 scale, now the space of v1, the basis function in this space, you will have now two basis functions. One will be phi of 2t and one is phi of, this is phi t basically, and this is psi t at scale 0. You have to just translate. There is no scaling. Okay, that's j is equal to 1. This space v1 will have two basis functions. One is phi of 2t, one is phi of 2t minus 1. Okay, so phi of 2t, so it will be like this: 0, 1 by 2, and 1. And then you shift it by half, it becomes like this. So these are the two pulses. Okay, so between 0 to 1 by 2 it is 1, then 1 by 2 to 1 it is 0 here. So if we shift it by half, so from 0 to 1 by 2 it is not 0, and between 1 by 2 to 1 its amplitude is 1. Okay, so what this equation is saying that all those functions which can be generated by using these two basis functions, they can be generated by using these two functions also. Okay, one scaling and one wavelet function at a lower scale basically. Okay, and the reason for this is that it means if you can generate all this set of functions from these scaling and wavelets, it means first you should be able to generate these two functions from these functions. Okay, so if you combine this, if you simply add these two functions, this and this, add them together, what you will get? So from 0 to 1 by 2 it is 1, and it is also 1, so you'll get 1 plus 1 by 2. Okay, and it is 1 from 0 to 1 it is 1, from 0 to 1 it is minus 1, so plus 1 minus 1 will get 0, so you'll get a function like this. Okay, and after adding you can scale by factor of 1 by 2. Of course you will get 1 as the amplitude. Okay, so this function can be generated from these two functions. If you simply add them, and after addition you multiply a factor of 1 by 2, you will get this pulse. Similarly, this pulse can be generated by using these two functions. Okay, so in that case you have to reverse it, because one function is like this, another function you have to reverse it, it will become like this. So this is phi of t, this is psi of t multiplied with minus 1, minus psi of t. So it will become minus 1, this is 1, this is 0, 1 by 2 and 1. So again if you add these two functions, so between 0 to 1 by 2 it is 1, it is minus 1, so minus 1 plus 1 it is 0, and after that it will remain 1 plus 1 2, and then scale by 1 by 2 you will get 1. So you will get a pulse. If you add these two pulses, you will get a pulse like this. It will be 2 in fact, and then you have to multiply it 1 by 2 factors, you will get it as 1. Okay, now these two functions, if they can be generated from these two functions, that means the set of all the functions which can be generated from these two functions, that is space of v1, that can be jointly represented by v0 and w0. Okay, and similar if you go to any other high scale, if you have v2 which is v1 with w1, now if you take j is equal to 1 scale, so you have two scaling functions, and w is equal to 1, you have two wavelet functions. So this is v2 as v1 with w1. Now j is equal to 1 and j is equal to 2. Now for j is equal to 1, the space is v1 scaling function, and for wavelet it is w1. So what are the basis functions here? Now it is at scale 1 for j is equal to 1. So you have two sets like this. Okay, so 0, 1 by 2 and 1, and this is 0, 1 by 2 and 1. Similarly, for the wavelets, you again have one is the basis wavelet scaled by a factor of 2, so it will become like this. It is 0 to 1 by 2 now only. This part will become 1 by 4. Okay, or you will have this phi t, another function is phi of 2t, phi of 2t and phi of 2t minus 1. Similarly, psi of 2t, and then when you generate psi of 2t minus 1, it is shifted by half, compressed by half and shifted by half. So it will become like this. It will go from 1 by 2 to 1, which is psi of 2t minus 1. Okay, so these two basis functions, they span this space w1, and these two basis functions, they span the space v1. For j is equal to 2, what is the span of v2? You'll have 4 functions. Okay, because j is equal to 2 means you have generated now psi of 2 to the power j minus k, this set, and j is equal to 2, it is psi of 4t minus k. So it is now this scaling function phi of t, which was 0 to 1 as 1, it is compressed by a factor of 4. So you will have a function like this. So 0 to 1 by 4, it will be now 1, rest will be 0. Then when you generate phi of 4t minus 1, it is shifted by 1 by 4. So another function. Then phi of 4t minus 2, another function. Then phi of 4t minus 3, another function. Okay, so these are the basis functions for this space. And again, like we have done previously, so these functions, they can be generated by combining these functions. Okay, it means any set of functions which can be generated by in the space v2, that can be represented by v1 and w1 and so on. Okay, so in general, any function if you take which is in L square R space, so that can be decomposed using a scaling function at a particular scale and rest of the wavelet functions. Okay, what it actually means is that if you have any signal, any function, if you take f of t, maybe like function like this, if you want to decompose this function in terms of the wavelets, what you have to do, you have to choose first a scaling function phi t, and then corresponding to this you will have a wavelet function psi t. Okay, so you have to first choose that, okay, which is the scale that we want to use for the scaling function. Okay, or you can say that this function, it can be represented by, suppose you for scaling function it's choose a scale j is equal to 0. It means you have this space v0, then rest will be covered by wavelets. Otherwise you can have v of suppose 5, then w6, w7 and so on, or you can even have v of minus 5, then it will be v of w of minus 4, then w of minus 3, so on. So you have one scaling function which basically is used to define the coarse information in the signal. So suppose you take j is equal to 0 scale. Okay, so j is equal to 0 scale, and if you suppose Haar wavelet, so Haar wavelet, you have a, if this function is suppose 0 to some length, maybe 0 to 4. So using this Haar scaling function, you will have, if at j is equal to 0 scale, you will have function like this, 0 to 4. Okay, and then you will add some wavelet function to it, then you will wavelet at j is equal to 1 scale, wavelet at j is equal to 2 scale, So by adding all those functions and multiplying those wavelets with some wavelet coefficients, you can basically generate this function. This is what wavelet transform is. Okay. So for scaling function, we have only one single scaling function which gives the coarse information or the average, you can say. Okay, the detailed information in this signal that will be represented by wavelets. So if you suppose take wavelet at g is equal to 0 scale, so mother wavelet, so you may represent it like this. Okay, then you combine these functions, this function, then you use another wavelets, you compress it, then you shift it by some time and so on. So multiply these signals with different coefficients, go on adding. So ultimately this signal will be represented in terms of phi t and psi t only. So for phi t you have a single scale, and for psi t function you will have other scales also. Okay. So let me take one example from this. So you have a test function here. This is a signal. This is a function which you want to decompose in terms of wavelets and scaling functions. Of course, in this case, he has decomposed in terms of scaling functions only, Hart scaling function. So it was actually a pure sinusoidal wave like this, and two discontinuous points are created in it. Okay, this is the test function. So if you represent this in terms of wavelets, scaling functions only. Okay, so we have seen that. Okay, we can also represent v0 and v1 with v2 spaces because it is a subset of v1, v2 is a subset of v3 and so on. So that can give you any square integrable function. That can also be done. Okay, so this is approximation in v0 space. In v0 space we have constant function only, which is generated from the Hart scaling function. Okay, then we have approximation in v1. Now in v1 scale we have two scaling functions, phi t and phi 2t and phi of 2t minus 1. So by combining those functions you get some approximation like this. It means this signal is basically approximated like this in this space. Then we have v2. Now in v2 we have j is equal to 2, so we have compressed by a factor of 4. Compression by a factor of 4 and translation by 1 by 4 steps. So we have 1 by 4th here, then 1 by 4th here, 1 by 4th here, 1 by 4th here. So okay, of course they're multiplying with some scaling or constants also. Then if you go to v3 space, now v3 means 3 is equal to j is equal to 3, so we have 2 to the power 8. So the steps are in basically translated in a factors of 1 by 8, compressed by 8 and steps by 1 by 8. So it gives a more close approximation. Then in v4, then v5, and finally this is approximation in space v6. So the v6 means you have 2 to the power 6. Okay, the steps, so this signal, this function, original function is compressed by a large factor and it is translated in very small steps. Okay, so at each scale and at each translate you multiply with some constant, so those constants basically they become your DWT like this. Okay, this is how you can decompose a signal in terms of scaling functions. And in place of scaling functions, so you can have another option that okay, you just choose in v0 space, you choose the phi t, and rest you can choose psi t wavelet functions. So that can also be done. Okay, this is what is multi-resolution analysis.